Okay, so example 3e. In this example, we have two random variables. They are independent. Okay? X is now discrete. It's going to be Poisson lambda 1. Y is also Poisson lambda 2. And we want to know, well, x plus y, the range of x and the range of y are countable. So the range of x plus y is going to be countable. So x plus y is discrete. So we'd like to know the mass function of x plus y, the sum of independent Poissons. All right, so x, it's Poisson, so it can be any non-negative any non-negative integer. That's its range, the non-negative integers. Y is Poisson, its range is also the non-negative integers. And so the sum can be any non-negative integer. So let's write that the range of x plus y is the set of non-negative integers. Okay. So what I want to know is for, well, what's another notation for this? I can just say n union 0. So for any n in either the naturals or 0, I want to know what is the probability that x plus y equals n. That's what I need to calculate to know the complete distribution of the sum. All right, so we can do it like this. Let's break it down according to the value of x. Okay, so I can write it like this. So what can x be? If x plus y is going to equal n, then x certainly can't be bigger than n because y cannot be negative. So x must be an integer between 0 and n. Those are the possibilities. And if x is equal to k, then for the sum to be n, y has to be equal to n minus k. Okay, so I have n plus 1 disjoint possibilities. And I'm adding up those probabilities. Okay, x and y are independent, so that probability becomes a product. So I have the probability that x equals k times the probability that y equals n minus k. All right, now I know the mass functions of x and y because they are Poisson. So the probability that x equals k is e to the negative lambda 1 times lambda 1 to the k over k factorial. And then for y, it's e to the negative lambda 2 times lambda 2 to the n minus k over n minus k factorial. Okay, and we need to manipulate this, simplify it. So anything that doesn't depend on k, I can pull that out. So I can pull out the exponential. So I have e to the negative lambda 1 plus lambda 2 coming out. And then I have the sum as k goes from 0 to n. And then I've got 1 over k factorial times n minus k factorial. And I have lambda 1 to the k, lambda 2 to the n minus k. All right. Now, when I look at that k factorial times n minus k factorial, it reminds me of the binomial coefficient. So maybe we can get somewhere if we had an n factorial on the top. But we can't put an n factorial on the top without putting it on the bottom also. So let's do that. And I can do it like this. So e to the negative lambda 1 plus lambda 2 times the sum as k goes from 0 to n of 1 over n factorial times n factorial over k factorial n minus k factorial, lambda 1 to the k, lambda 2 to the n minus k. All All right, then we can pull out the 1 over n factorial because it doesn't depend on k. So I have e to the negative lambda 1 plus lambda 2 over n factorial. I have the sum as k goes from 0 to n of n choose k times lambda 1 to the k, lambda 2 to the n minus k. And now that expression, this one here, that sum, we can recognize that. That's from the binomial theorem. So that's just lambda 1 plus lambda 2 to the n. So this whole thing can be rewritten as e to the negative lambda 1 plus lambda 2 times lambda 1 plus lambda 2 to the n over n factorial. And that's the mass function of x plus y. But you should recognize that mass function. That's the mass function of a Poisson with parameter lambda 1 plus lambda 2. So in other words, x plus y is Poisson with parameter lambda 1 plus lambda 2. So what this example shows is that the sum of independent Poisson random variables is a Poisson random variable. And the parameter of the sum is the sum of the parameters. Okay. So the next example, I don't want to go in detail, just tell you the result. It's example 3F. It's the sums of independent binomials. So, and that there. So I'll just state this as a fact. If x, and you can read the example, it's example 3F. If x is binomial NP and y is binomial MP, and they are independent, then that implies that x plus y is binomial as well with parameters n plus m p. And this one, you can check it, and it's in the book if you want to read it, and you check it in the same way that we did the last example. And hopefully it makes a lot of intuitive sense when you think of binomial NP as counting the number of successes in n trials. So you count how many successes in the first n trials, then you have another set of m trials independent from the first with the same probability of success, and you count the successes there, and then you add them up. And what you've got is the total number of successes in n plus m trials. Okay. So that's 6.3, sums of independent random variables. 6.4, well, let's not do 6.4 yet. Let's take a detour. We want to take a detour and look at some notes. Okay, so what I'm going to talk about right now, I'm just going to do this briefly and then come back to 6.4, is not in the book. This is coming from a set of notes that I've written. And as of right now, there is no link to them on our course webpage. But by the time, so right now meaning the time of me recording this, by the time you watch this, there should be a link. So this is a set of notes titled Conditional Densities, Mass Functions, and Expectations. So as a reminder, a couple of reminders about joint distributions. So if x and y are discrete, then I can talk about their joint mass function. The joint mass function, P of xy, is just the probability that x equals x and y equals y. Right? And sometimes we write that as P sub x comma y to indicate that this is the, so aka P sub capital X, capital Y, to indicate that that's the joint mass function. On the other hand, if x and y are jointly continuous, right, then you have a joint density. And the joint density has the property that the probability that the point xy is in some region in the plane can be calculated as the double integral over that region of the joint density. Now, one thing and that's both in the book, and so I'm just recapping. But one thing that's not in the book is what do you do when you have two objects that you need to consider jointly, two random variables. You have to consider them jointly, but one of them is continuous and one of them is discrete. Okay, so this is not, they don't talk about this in the book, and yet you're expected to know it or perhaps understand it intuitively because there are homework problems, exercises in the book where you really need to be using this, but it's not laid out explicitly. So this is in section 3 of those notes that you will have a link to. And this is what I want to define right now. I'm not going to go through all of section 3. I just want to define this object. So let's suppose x is discrete, okay, and y is continuous. Okay. Then we can have what I'm just calling in the notes, I just gave it this name, a joint density / mass function, because it's kind of both. It's a density in one variable and it's a mass function in the other. And it's going to be a function, f of xy. And it's a function where if you want to know the probability that x is equal to some little x is discrete, and y is an element of some set, maybe an interval, then you can compute it by doing the integral over a of f of xy dy. So if you can find a function that does this, then that's the joint density mass function of this pair of random variables, where one is discrete and one is continuous. Now, if x is discrete, then it's got a range. So the range of x is, well, every random variable has a range, but it's got a countable range. Let's say the range is x1, x2, and so on. Then one of the properties of a joint density mass function is that if you do the sum over all the i's and integrate from negative infinity to infinity, f of xiy dy, then you get 1. So let me scroll up for a second. With the joint mass function, if I sum, so put this on a little side. So if r of x is x1, little x2, and so on, and the range of y is little y1, little y2, and so on, then if I sum over all the i's and I sum over all the j's of p of xi, yj, I'm going to get 1. So when you do the double sum over all the possibilities of a joint mass function, you get 1. Just like with an ordinary mass function, if you sum just a single sum over the range is going to give you 1. And with a joint density, if you integrate over, so here you're integrating over r, if you integrate over the whole plane, r2, you're going to get 1. So that same property, the form it takes when you've got a mixture here, if you've got a discrete and a continuous together, is that the variable that's representing the continuous one, you want to integrate that over the whole real line, and the variable representing the discrete one, you want to sum it over the entire range of that discrete random variable, and then you'll get 1. Okay. And you can do it in either order. You can put the sum on the outside, or you can put the integral on the outside. So it's like a double integral where you reverse the order of integration. You can think of these things, the sum and the integral, like just both being integral type operations, and you can reverse the order, just like you reverse the order of a double integral. And this is a side note, it's an advanced thing that is, you would learn probably you'd have to go to graduate school to really see it properly, but a sum really is an integral. There's a generic concept of integration where The integral that you do from calculus is a special case, and the sum, when you're doing a series or any kind of sum like that, is also a special case. So this really is a double integral if you understand the word integral in a very generic sense. But like I said, that's a really advanced topic. But just a side thing in case anyone is interested. Now you can get marginal objects out of this. So if you want the mass function of x, then you just integrate out the y. And if you want the density, so this is the mass function of x, and this is the density of y. If you want the density of y, well, you can't integrate out the x, you sum out the x. And what you're left with is the density. So just like with a joint density, if you integrate out one variable, you have the density of the other one. Well, this is the same thing, except when you can't integrate out the x, you sum it out. Okay. And just like with joint densities and joint mass functions, if x and y are independent, then this joint object, this joint density mass function, is the product of the mass function of x times the density of y. So this is kind of a missing piece of the puzzle up till this point, and we're going to need it now once we start in talking about conditioning. Okay. So this missing piece of the puzzle is at the beginning of section 3 in those notes, and like I said, by the time this you watch this video, you should have a link on the course webpage to those notes. All right, I'm going to stop here, and then we'll pick up with 6.4.